So I'll be talking about a couple of joint works together with Kaimin Chung and Rafael Paz on large-scale secure computation. Okay, so you've been here, maybe not, for the whole week. And we've been talking a lot about situations where, for example, Alice and Bob want to compute something together, maybe some AES encryption. Or say that there's 5 of us in a room and we want to compute some functionality together. For this talk, I want to shift gears a little bit and focus. Can you hear me? Okay, so you saw the pictures. So for this talk, I want to focus on the setting of large-scale MPCs. So what do I mean by this? I mean, we want to think about scenarios with lots of parties and lots of data. Okay? So the first question is, what sorts of things are changing in this scenario? So when we talk about efficiency of MPC protocols, we talk about the communication requirements, how much overhead in memory and computation. So how do we need to look at these differently potentially? Okay, so for example, for communication, you've heard all sorts of talks and probably know this area, but there's tremendous amounts of work and improvements and success in minimizing, say, the number of bits that we communicate or the number of sequential rounds of communication that are needed. But interestingly, if you think about a setting with a small number of parties versus a large number of parties, something that we haven't really looked at much is who am I actually talking to? So if Alice or if Bob is the only person in the world, obviously that's pretty clear. But it turns out that in protocols, so if you look throughout kind of the history of MPC, nearly every protocol has the property that everybody ends up speaking to everybody else. Okay, so again, if 5 of us sitting in a room, not a big deal. Now we've got 10,000 parties running a protocol over the internet and requiring each pair of us to actually initiate a secure communication channel becomes somewhat impractical. Okay, so one thing to look at here is the new metric of locality of communication within multi-party computation. So here, we want to consider the total number of parties that we actually need to talk to, for example. Okay, how about memory? So one difference between 2 parties and lots of parties is that if we each come with some information, some input, say, the total combined amount of data can be huge in this setting. So something we really want to focus on is that no individual party has to carry the burden, say, of storing everybody's data comparable to everybody's inputs combined. Or also even beyond memory, but working in general, we want to balance the load. So specifically for memory, we want the requirements, for example, grow as his fair share of the computation space required, and something comparable to his own input size. Okay, but the point that I actually really want to drive home here is that when we're looking at large-scale computations, sometimes the types of programs that we want to compute are different. Okay, so we've been hearing a lot of protocols, again, kind of a cookbook. So you have some function you want to compute securely, and you first convert it to a circuit. And now there's all sorts of different techniques once you have this in the circuit form of how to convert this to an MPC protocol. And as it was mentioned, trying to actually optimize and get smaller, tighter circuits to describe this function f can give you much more efficient protocols at the end of the day. Okay, but suppose that f is some sort of program, okay? Maybe it has a very tight description. Maybe it does binary search as different pieces, things of that sort. For a lot of these programs, to convert this first to a circuit is a huge overhead. Okay, even back to binary search, for example, logarithmic running time, right? Very simple, very clean. Convert it to a circuit, and automatically you already have a blow-up of the entire size of the database. And this is true for general conversions. Okay, so take a step back, go back to Theory of Computation 101. What are sort of our options here? So circuits are great. They give a lot of good properties, especially for when you're trying to compute things securely, say fixed topology, things of that sort. But how can we try to push this further? Okay, so we all know and love Turing machines. But what else? Okay, RAM machines. So RAM machine model, again, now the benefit here is that you get random accesses for free. So already, for example, with the binary search, now the size goes back to logarithmic. Okay, but I want to push this even further in this talk, okay? I want to talk about parallel RAM machines. So here, this is a model where you have a collection of CPUs, potentially which could be some inactive at various points of computation, as long as that's fixed a priori. And each CPU can independently be running computations locally and accessing shared memory. Okay, so what's the point? In the large-scale computations, we want to do things that use these, that really leverage random accesses and leverage parallelism. For example, say we want to do a secure computation where we're looking at people's genetic data. Well, if I'm computing on my genome, I'm certainly not going to want to scan with a Turing machine, along the whole thing. So although circuits and potentially Turing machines, so circuits have given us great starts and have done, allow tremendous amounts of secure computation in progress. I want to try to push beyond this and say that hopefully we can try to get to, circuits are not appropriate. That's the claim. Okay, so that's not all that exists. In fact, Benny Pinkas talked a little bit yesterday about secure computation for RAM programs. But the downside here, so interestingly enough, actually in some cases, circuits might be better than RAM programs. Why? Because you lose parallelism. Okay, if you have some sort of program that can be efficiently computed in parallel, to convert it actually to a RAM program, now you're losing that benefit. So this is why in this work, we took a look and we tried to do, can you directly achieve secure computation for parallel RAM programs? Sort of, in the asymptotic world at least, the best of both worlds of circuits and RAM. All right, so what exists? What is there right now? Tons of fantastic work in the circuits model. Okay? Actually, I even want to make a special call out here to a line of work known as scalable MPC, starting with Damgaard and Ishai in 2006. And they're actually looking at some overlap of questions in the large-scale setting where, say, there's a lot of parties. But again, it's still in the circuits model. In the RAM model, there's been kind of a handful of works somewhat recently looking at two-party computation protocols. So this is what Benny was mentioning yesterday. But unfortunately, the downside of those is that when the number of parties grow, actually they don't scale particularly well. For example, so this essay that I'm referencing is actually even just an aside in a paper of Damgaard et al. For Oblivious RAM. And they say that in fact you can do, say, multi-party computation using some of these tools. But if you just look at this suggested construction or even some very simple extensions of it, you have the property, unfortunately, that there's individual parties that have to maintain data the size of everybody's inputs. Okay? And in the PRAM model, nobody's looked at this. Good. So what's the goal? We want efficient MPC for parallel RAM programs that also takes into consideration some of the other metrics that I was mentioning. Okay, and I want to put a disclaimer here. I'm going to be talking completely about asymptotic efficiency. There's obviously a clear gap between some of these analyses and what the practical implementations would be. But I think that this is really exciting as a first step in order to try to see, can we get the asymptotic efficiency down? And maybe that will serve as a kind of opening a door for big improvements in the future. Okay, so say we have n parties, all of us here, even more, and we want to compute a sequence of parallel RAM programs on inputs. So what can we hope for? So we want that somehow the time steps, the parallel complexity of the protocol is going to be comparable to the parallel time of the PRAM. We want the computation to also scale with the computation size, the size of the PRAM program, the computation required. And beyond that, I want to balance the load. Also, as we mentioned, the memory requirement here, I want this to scale with kind of one person's input and the fair share of the computation storage. Okay, so I do want to mention something. Unfortunately, something that you can't avoid, actually, is that if you want to do secure computation for general programs, it has to be the case that everybody has to at least touch every bit of their input. So to see why this is the case, suppose that the function that we're computing is some sort of private information retrieval function. Okay, so somebody's secret input is, say, a particular bit of somebody else's input, and she should learn just that bit, and nobody else should learn anything else. Okay, well, in order to actually give security here, if you don't touch a bit of your input, you know that wasn't the bit that was requested. Okay, so this is kind of an unfortunate requirement here, but as we'll see later, we'll be able to do this in an amortized sense. So we only have to pay this once up front, and then we can continue evaluating programs with a tighter computation requirement. Okay, and ideally, somehow, maybe we could do this by only talking to one other person, or maybe a handful of other people. Okay, so these are sort of what we can hope for. And so combining a couple recent works of ours, we get something pretty close to this. Okay, so first of all, this O tilde notation is hiding polylogarithmic factors in n, where n is the number of parties. But here, these are essentially what we wanted. Given this one-time preprocessing phase. So again, the preprocessing phase is reusable. We only have to do it once, and then can continue making use of that. But this is where this cost of having to touch your input is going to come in. And in fact, actually, in our construction, so we have a little bit extra requirement. There's some interesting questions there if we can get that down. But we currently require each party to make one short broadcast. So not very many bits, but it needs to be sent to everybody. Okay, and this construction is assuming static corruptions in a synchronous network. Somewhat different from what we've been seeing mostly in this workshop is that this is in the setting with honest majority and unconditional security. So there's actually no computational assumptions here. So I think actually that this setting was very interesting to study. So as Claudio mentioned in his talk, there's a lot of benefits about unconditional secure or information theoretically secure, there we go, protocols. For example, that the computations tend to be much cheaper than cryptographic operations. We don't need things like exponentiations, just stuff like simple secret sharing. Okay. Good. And in fact, so in this setting with unconditional security, if you're familiar with the area, that means, unfortunately, with the state of the art, this parallel complexity is actually going to correspond to the number of sequential rounds of communication. It's a huge open problem. Would be fantastic if anybody could figure out how to get that down below. Would really be an amazing result. Okay. And actually, so one last thing to point out here. So if you, in this setting, if you don't have what's known as a broadcast channel, where you sort of get broadcasts for free, then 2/3 is required. So we require a little bit more than that. And so I did tell you, actually, we use one broadcast, but you can implement that just with a broadcast protocol. Okay. So anyway, takeaway message here is that we have unconditional security. And what we achieve is essentially what we would hope to achieve with polylogarithmic overhead. All right. So I won't be able to go into all the details, but I want to tell you some parts about the construction, and at least some of the high-level ideas. Okay, so luckily I can speed through this part. So how do MPC protocols typically work? And here I'm focusing on multi-party protocols. So this is more GMW style as opposed to YAO. Okay, so step one, each party will secret share its input among everybody else. For example, using Shamir secret sharing. And in step two, now we just go through the circuit gate by gate, and for each gate, we do some computation, either locally adding shares or running some, say, small miniature protocol to compute a gate. Okay. So what about the large-scale setting? Lots of data, lots of parties. already we see problems here. Okay, in step 1, we immediately have everybody talking to everybody else. And if I'm secret sharing my input among everybody, that means that everybody's holding this size of data that's comparable to everybody's input. In the second step, if we're going through and evaluating the circuit gate by gate, then obviously the computation is going to be comparable to the circuit size description. So let's consider, for now, let's look at kind of an easier or a simpler intermediate step. So forget about lots of parties, but let's just focus on large data. So really the goal here, I'm not going to care so much about the problems in the first step, but really we want to get the computation requirements of the protocol down to the PRAM complexity of the program. Okay? Okay, so let's start delving in here. So how does the PRAM actually work? What is the construction? So we have some collection of CPUs, and the program itself is basically what's going to be within this box. Okay, so it'll be a sequence of sub-computations that will work sort of as follows, and will be performed in parallel with all the CPUs. Okay, so let's follow kind of the computation of these pair here. In the first step, they'll do this sub-computation, and the output here will be some state to continue to the next part, and some address in the shared memory. This address tells the CPUs where to look in the shared memory database. They look up this information and use it as the input to the next part of computation. Okay, and this keeps repeating. Okay. So here's the first idea for how to do secure computation on this PRAM structure. Okay, so for each of these small sub-computations, we can just compute this as using a regular, say, MPC for circuits. Okay, so this should be Ostrowski Shoup instead of Lou, sorry about that. But so this idea is not new. This is something that's been considered, and is in fact, so in these was in the context of RAM programs. So let's be more explicit about this. So first of all, each party will secret share his inputs among all parties. I'm denoting this here by kind of these shades of green, which will say add up in some way to this database. And now we'll just step along in this PRAM computation via small-scale MPCs. Okay, so for the first computation, all the parties will essentially be emulating these CPUs in parallel. So all of these will be going on at the same time. Okay, but I'm just focusing here on one of the particular CPU computations. Okay, so the output of this small-scale MPC will give everybody some secret share of the state that we can transfer to the next one, and everyone will get the address in the clear, say. Okay. So I have the address. I'll just look, say, at that address in my local database, my secret share of everything. And so remember that all these say secret share whatever address is actually wants to be accessed in the program. And now we can use the information here and the state as the inputs to the next MPC. So this is great. This makes good progress. For example, you see that the only information that the parties are seeing now are just secret shares of the state information, the secret CPU information. So that doesn't reveal anything. And these addresses. So note that we kind of needed these addresses to be in the clear so that people knew where to look at. And that gave us this cheap random access. So we didn't have to, for example, scan or look at everything in the individual memory. But unfortunately, this comes at a cost. Okay? These addresses, the address patterns, the memory access patterns, can actually leak information about the inputs. Okay, for example, so look at this sort of toy example here, just to drive the point home. Go back to binary search. Say that we're running some program that's just binary search for a fixed value, 100. Okay, now I don't see what's on the right, I don't see what's actually going on, but say I see this sequence of memory access patterns. Okay, so whoever was doing this looked at memory 4, looked at memory 6, and then stopped. This is actually revealing quite a bit of information about the data that's held in here. Okay, for example, we know that this middle point was less than 100, and that this value was actually even equal to 100 because we stopped early. So what do we want to do? This is a great approach from the previous slide, but we somehow need to hide information that could be leaked from memory accesses. So what we want is to somehow be able to take the PRAM program and compile it to one with oblivious accesses here, where that means that the memory access patterns are at least appear independent of the data. Okay, and in general, we'd like to do this sort of, instead of looking at specific programs, we want to figure out how to do this in general. So this is also something, in fact, Benny talked a bit about ORAMs yesterday, but this goes back even to 79 with Pippinger and Fisher. They showed that for Turing machines, actually you can convert a generic Turing machine to one with oblivious memory access patterns with logarithmic overhead. Here, when I talk about overhead, I'm talking about the size of, say, the memory. Okay, for RAM programs, going back to Goldreich and Ostrowski, and as Benny mentioned, particularly in recent years, there's been a lot of work of getting even more, better, more efficient ORAM compilers. So right now, this is also probably logarithmic overhead. And in this work, so as one of the kind of the big tools that we present is the first oblivious parallel RAM compiler. Okay, so what's the point here? Again, if I have some parallel RAM program, I can always just use an ORAM compiler, but that automatically means that I have to first convert it to a sequential RAM program and then use the tools that existed before. Whereas we give here this polylog overhead corresponds both to the amount of computation total, but also the parallel complexity of the program. And I'm not going to have time to talk about the solution, but I just want to say a little bit, what are the challenges here? So if you remember, Benny spoke a bit about some of these tree-based ORAM schemes. Don't worry if you didn't see it. Just kind of the point to keep in mind is that I'm representing here, so memory, for example, is stored in these nodes of a data tree. And whenever you make an access, so say I want to access some data item, I'll know which path it is along the CPU. And the CPU will access the entire path along the tree to that data item. Then when the data item is returned, you return it back to the root of the tree. Okay, so now what about the parallel setting? So if you have multiple processors trying to do this sequence at the same time, you automatically have a problem. So if they're looking at different data items, maybe that's okay. But suppose they want to access the same item or some sort of correlated item. In these solutions that exist in the sequential RAM case, this is immediately a problem, okay? Because both of the processors will access the exact same path in the tree, which reveals this collision. Okay, so how do in the standard ORAM schemes, this is sort of avoided. This problem is taken care of by after you do an access, you assign the data item a new path, and you start moving it around over time. But we can't afford to do that directly. We can't have an access and then move, and then an access and then move. And at the same time, it seems like trying to store multiple copies at various parts of the tree is going to be a little bit of a, maybe it's an interesting direction to go into, but you have to make sure that if you try to do that, that you maintain consistency. So for example, if one CPU is writing a copy over here, it better be that when the other CPU is accessing the copy, that he also gets that value somehow. Okay, so I'm unfortunately not going to have time to talk about this, but ask me about it afterward. Good. So let's put the pieces together here. So what is the protocol? And again, this is a setting where I'm not really caring about how many parties. I'm just trying to get the complexity down to the PRAM complexity. So the first step, you do the standard secret sharing. In the second step, you take your PRAM program that you actually want to compute, and you compile it using this oblivious parallel RAM compiler. And in the final step, we do what we did before, where we emulate each of these subcomputations via small-scale MPCs. But here, the fact that the addresses are being leaked is not a problem, because we've done this compilation step. We know that these don't leak any information. Okay. So let me just kind of point out that our main contribution for this piece is the new Oblivious parallel RAM compiler. Okay, so what about when we want to go back and actually consider lots of parties? So we've got, first task, check. But what about the problems that we had before? So we had the issue that everybody was talking to everybody. We want to get locality down. We also want to get the memory requirements down. So note that in this construction, everybody was still storing a secret share of everybody's input. But at the same time, while doing these, we want to get load balancing. Okay? So for example, we could always just say elect a small committee of people and run the other protocol. But that means that those small collection of people are unfortunately doing all of the work and storing all of the memory. And this is for another time. I've got 5 minutes left, so definitely for another time. I just want to leave you with a little bit of a teaser. I like this work a lot because one reason is because it has a lot of different kind of cute ideas and different fun tools to work with. So for example, what are some of the tools that we really need to use? We do techniques with electing committees. Okay, so instead of having everybody, your secret share your input to everybody, we'll instead have some small committee of people, and you'll secret share it just to some committee. We have, so this Oblivious parallel RAM, so if you think about this as different entities, say, as these CPUs and as even just these blocks of memory, we'll actually emulate each of these different pieces via a separate committee. So this will allow us to get load balancing. Actually, let me take that back. This will allow us to get memory balancing, but not load balancing, okay? Because the CPU's committees are going to be still doing all the computation. So to get load balancing, on top of some of these things, we have a semi-generic way that basically, as a committee is assigned a job, and once it's worked enough for a job, it'll pass the job to somebody else. And if you do this in sort of a sufficiently random way, in a nice way, and you have to be careful, for example, about when to pass and how much state is it that you need to pass, you can actually balance the load. And finally, in order to get locality while maintaining everything else, we actually kind of enforce another communication network on top of everything. So you can do some neat things with load balanced routing on this new communication network. Okay, I want to sum up with just some future directions. I left this pretty high level here. The first is, so as I like to think, UpRAM is the new ORAM. In fact, this is attributed to me. But I really do think, in all seriousness, that trying to get the parallelism, right now, our current solution is a proof of concept. I think there's a lot of exciting work to try to get this to the equivalent efficiency to, say, even Oblivious RAM schemes. So there's been a lot of work, as I mentioned, on getting ORAM to be very efficient, and also in using it in different applications. So for example, in security groups are building systems using ORAM techniques, and I think that if we can get OpRAM to that level, that this is a fantastic opportunity. And also, so there's so many directions. Here we've I view this as taking a first step. So people have looked at large scale in various senses before, but in particular with this PRAM and also trying to get locality and load balancing and everything. But we did this within, for example, a specific setting. So with this 2/3 honest majority and a synchronous network. And I think there's a slew of exciting questions of trying to push this both in the theoretical side, and also hopefully eventually this will start going toward real practical directions. So if you're interested, please ask me about it, and I'd be happy to talk to you. Thank you.